Hi, this is John Whitaker for the Mathematical Analysis 2 class. And this is our 22nd video lecture, and today we want to pick up where we left off, talking about the ratio test. And I suspect what we'll do is we'll complete the proof of the ratio test, do a quick review about some of the series tests that we've had and what kind of series they talk about, whether complex or real valued series. And then we'll also do some examples during this lecture, and then we'll move on to power series and talk a little bit about them, maybe including the radius of convergence. So let's recall about the ratio test. What it says is that this series, the sum is n runs from 1 to infinity of a sub n. We're thinking of a sub n being complex numbers. We're going to say that converges if, I made a mistake here, if the lim sup is n runs to infinity. Lim sup of the norm, or the absolute value of these complex numbers of a sub n plus 1 over a sub n is going to be less than 1. And it diverges if this absolute value of the ratio of these complex numbers is greater than or equal to 1 for all n bigger than or equal to n sub naught, where n sub naught is some fixed integer. So we want to prove this theorem. Okay, so we'll start the proof. And we'll suppose that the lim sup of a sub n plus 1 over a sub n is less than 1. Okay? Suppose that. Then we can find an integer, big N, so we're thinking of it as a natural number, such that this absolute value of this ratio, a sub n plus 1 over a sub n, is going to be less than 1, or less than, I should say, b, for all n I made a mistake. I wasn't paying enough attention. So let's suppose that this lim sup is less than 1. Then we can find an integer b and a number. Find an integer n, I should say, and a number b that's bigger than 0 and less than actually it's going to be, bigger than 0 and less than 1. Okay? Such that, here we go, that this ratio, the a sub n plus 1 over a sub n in absolute values, will be less than b for all n bigger than or equal to big N. So in particular, we have that a sub n plus 1, that absolute value, will be, let's see, less than, so I'm looking right here, and I'm using little n equal to big N. A sub n plus 1 is going to be less than b times the absolute value of a sub n. Yes. Okay, so that's what we have. We can kind of extend that. Also, a sub n plus big N plus 2 inside the absolute values is going to be less than b times a sub n plus 1 But this guy is less than, we'll go right to the b. This guy is going to be less than b times the absolute value of a sub n. So the b that I would get from here, and this b makes b squared, less than a sub n inside absolute values. Big N here. We continue like this. And so what we get is a sub n plus p inside absolute values is going to be less than b to the p times the norm, or the absolute value of a sub n. So, this is true for all n bigger than or equal to this big N. So for all n bigger than or equal to this big N, what we have is a sub n is going to be less than a sub big N times b to the little n minus big N. That's from the previous work we just had. So, for all n bigger than or equal to this big N, the absolute value of a sub n is less than, here we write this as b to the minus big N. Then I'll write down the absolute value of a sub big N times big B raised to the little n. That's using rules of exponents. Okay. Note the sum of b to the minus n, as n runs from 1 to infinity, times the norm of, or that's the value of a sub n, times b to the n, little n, converges. And the reason it converges as b is less than 1. So we're thinking here b to the n. What this is a geometric series. It's a geometric series where you have this constant times b to the n. Okay? And so, so by the comparison test, that means that the sum of the a sub n's must converge, which is what we want to show in this case. And so that's the proof of part A. The proof of part B is if we let a sub n plus 1 over a sub n inside absolute value be greater than or equal to 1 for all n bigger than or equal to some n naught, then, okay, well, before I say then, let me just write a side note. We are assuming in the statement here that a sub n is never 0. That's something to keep track of. And that's true for all n bigger than or equal to n sub naught. So we have that a sub n plus 1 inside absolute values is greater than or equal to a sub n, and that's for all n bigger than or equal to c sub naught. Okay? Now, note that a sub n being different from 0, again, we'll just make that plain here. That's true for all, really I said for all n bigger than or equal to n sub naught, but it's really true for all n element of natural numbers, so element j. And what I want to do is claim that the limit as n goes to infinity of a sub n is different from 0. So we need to prove that claim, and then by the divergence test, the series of a sub n diverges. So here's the proof of the claim. Now, note, a sub n sub 0, that's different from 0. So we have that a sub n inside absolute values is less than or equal to a sub n sub naught. And this is true for all n greater than or equal to n sub naught. Okay? Thus, what we have is there exists a natural number, exists an n, I would say a natural number, such that for all n bigger than or equal to this big N, the absolute value of a sub n will be greater than or equal to a sub n naught, which we'll think of as like an epsilon. Okay? And since that's happening, okay, then that forces that the limit as n goes to infinity of the a sub n's have to be different from 0. You know, if it were equal to 0, this absolute value will be less than or equal to absolute value of a sub n minus 0 will be less than or equal less than any epsilon that you give me. But if I give you this epsilon, hey, this guy's always bigger than this. So it's never less than this quantity. All right, so since the limit as n goes to infinity of a sub n is different from 0, then by the divergence test, this series a sub n diverges. And that ends the proof of the ratio test. Okay. Well, next, I want to give a summary here in terms of facts that we've mentioned, tests that we've talked about for series, and say whether they apply to complex or real sequences or series of real numbers, complex numbers. So the first one I want to look at is the quotient criterion. And this series test is for complex series. to the divergence test is for complex series. Three, this series of a sub n, with a sub n being greater than or equal to 0, converges if and only if we got to bound it. If the sequence of partial sums is bounded is for a real series. I think I call this something like the dichotomy theorem. Next thing we'll talk about is that comparison test. And it had two parts. And so, just as notes, the comparison test A is for the part that had to do with A. It's called was for complex series. You might remember it had to do with the absolute value or the norm, and so that's for complex numbers. Series AN, okay, but CN is a real number, okay, that's involved here in part A. In part B, AN, BN, those terms of sequences that were involved in series are reals, real numbers. Then, fifthly, the geometric series, that's for real numbers. Sixthly, this Cauchy theorem about this 2 to the k, a sub 2 to the k series, telling us whether or not the series of a sub n converges or not, a sub k converges or not, is for real series. And then we got the root and ratio test. So 7, root test is for complex series. And ratio test is for complex series. What I'd like to do now is to look at some examples where we're trying to determine whether a particular series converges or diverges. And my examples will primarily, maybe essentially, just deal with real number series, but here's the first one. So here's some examples. So someone might want to know, this is my first one. We have a series as n runs from 1 to infinity of 3n plus 1 over 4n plus 7. And the question is, converge or diverge? That's the question. Well, the way that I would handle this is that here, one of the things that has to happen for it to converge is that the limit has to be 0. But if you notice in this problem, the limit is n goes to infinity of 3 to the n plus 1 over 4 to the n plus 7. Well, this would be infinity over infinity, so I'd use L'Hopital's rule, and that would yield the limit is n goes to infinity of 3 over 4, which equals to 3 over 4, which is definitely not 0. So this, let me write it up over here. This series diverges this series diverges by the divergence test. Okay, another example I'd like to look at is the sum as n runs from 1 to infinity of 1 over n to the 7th. Again, what we want to determine is whether this series converges or not. And so the answer is, this converges by the p-series test. It's a p-series with p being equal to 7. So it converges by the p-series test because 7 is bigger than 1. Okay, another example, and a similar example, if we look at the sum as n runs from 1 to infinity of 1 over the square root of n, we want to know whether this converges or diverges, but it can be rewritten as the sum as n runs from 1 to infinity of 1 over n, to the 1/2 power. That's a 1/2 power. And then that's a p-series, but the p is less than or equal to 1, so I'll write down, which is a divergent p-series. So the p-series test answers whether this example converges or not. Okay. Another example is the sum as n runs from 1 to infinity of 1/4 raised to the n. Again, our question is, does this series converge or diverge? Well, this is a geometric series. This converges. It's the convergent geometric series. As again, x is equal to 1/4, which is less than 1. And then another example is the sum as n runs from 1 to infinity of 3/2 raised to the n. And this, again, is a geometric series. This is a divergent geometric series. A sixth example is that if I look at the sum as n runs from 1 to infinity of 1 over n squared plus 1, and I want to decide whether this converges or diverges, it's not quite a p-series because of this plus 1. But here's what I want you to notice. Note that n squared plus 1 is definitely greater than n squared, and that's true for all n, for all natural numbers. N. So that means that here we divide by n squared, and we divide by n squared plus 1. So you get 1 over n squared is going to be greater than 1 over n squared plus 1. And so the norms of this guy is less than that. The absolute value of this is less than that. And that's for all natural numbers. And so by the comparison test, since the sum of 1 over n squared is a convergent p-series, then the sum as n runs from 1 to infinity, 1 over n squared plus 1 converges by the comparison test. Another example I'd like to look at is this series. So the series as n runs from 1 to infinity, 1 over n minus 1/2 times the square root of n. Okay. Now, we want to know if this converges or diverges. I'm going to tell you that it diverges. It's a lot like a p-series, and I think that's what we can compare it to. So, so here the first thing to do is to note that n minus 1/2 the square root of n, that's going to be less than n. That's true for all natural numbers. And so if I do a division both sides by n and also divide by n minus 1/2 the square root of n, what we get is that 1 over n is going to be less than 1 over n minus 1/2 the square root of n. Now, since this diverges in terms of a series, then this series 1 over n minus 1/2 square root of n diverges. Now I'd like to look at another example, 8. It says, what about this series as n runs from 1 to infinity of 3 to the n over n factorial? And a good way to determine the convergence or divergence of this particular series is to use the ratio test. So here we're going to converge or diverge. And we will use the ratio test. So in particular, what we'll note is that the lim sup of a sub n plus 1 over a sub n will be equal to the lim sup. Okay? And so here, this will be of the absolute value of 3 to the n plus 1 over n plus 1 factorial, through this table, all divided by, here this will be 3 to the n over n factorial, and that's equal to the lim sup here. We have the absolute value. We'd have 3 to the n plus 1 over n plus 1 factorial times the flip, of course, of this other fraction. So I'd have n factorial over 3 to the n. And that's equal to the lim sup. The n runs to infinity, lim sup here. This would be the absolute value. Well, we have some cancellation. I just have 3 in the top, and in the bottom, I just have n plus 1. And the absolute value of this is just 3 over n plus 1. And lim sup of that's going to be 0. So that's less than 1. So by the ratio test, this series is going to converge. Let me write that down. All right. So by the ratio test, this series converges. Let's look at another example, our last example. And here's what it says. We're going to look at the sum as n runs from 1 to infinity of n over 2n plus 3 raised to the nth power. We want to know, does this converge or diverge? And a good way of trying to determine that is we will use the root test. Kind of what it prompts me to use the root test is because we have something raised to the nth power, so the root test probably will be very effective here. And so here, what we note is that the lim sup of the nth root of the absolute value of this guy, which is just itself, so n over 2n plus 3 raised to the nth power. Well, the nth root and nth power will cancel each other, so we're talking about the lim sup of n over 2n plus 3. Well, that's going to be equal to 1/2. Okay. And so the root test is going to tell us that that series converges. Let me write that down. That is converged by the root test. Okay, now I want to switch gears and go into what's known as power series. And so here's the definition. It says given a sequence of complex numbers let's call them C sub n. The series sum, and here we're going to let n go from 0 to infinity, of C sub n, z raised to the n, is called a power series. And we're thinking of z being a complex number as well. And to clarify certain items involved in this definition, got a few more words to write. Namely, the numbers C sub n are called the coefficients of the series, and z is a complex number. What we're going to be concerned about, what we want to know, for what values of z will this power series converge or diverge. But we're really interested in convergence. And it doesn't converge, it diverges. Now, what seems kind of clear to me is that the z sub n's are the same in the power series. What changes are the C sub n's and what the values of z can be for the convergence. So the C sub n's are going to determine, if you will, restrict what values of z we can have in there for convergence. Okay. Here's a theorem that helps us make that type of decision about convergence or divergence. It says, given the power series sum C sub n, z raised to n, we put alpha equal to the lim sup n runs to infinity of the nth root of C sub n, its absolute value, and r is going to be equal to 1 over alpha. Now, this lim sup is going to exist to some extended real number. Okay, it might be infinity, it might be minus infinity, but it exists. And here, I'll say as a parenthetical expression, if alpha is equal to 0, so we can talk about r, then we're going to let r be equal to infinity. Okay. If alpha is equal to infinity, then r is going to be equal to 0. R will be equal to 0. You know, I said, it's an extended real number, but of course, this is going to be a positive or non-negative number, so the lim sup can't be less than 0 in this case. Okay? That's what we have. So R is going to be some non-negative number. I haven't completed the statement yet, so we just got some terminology here. So the theorem concludes with then the series C sub n z raised to n converges if the norm or absolute value of z is less than r and diverges if the norm of z is bigger than r. And then it's inconclusive if we don't have an answer if the norm or the absolute value of z is equal to r. Okay, but here, let's look at the proof of this. We'll let a sub n be equal to c sub n times z raised to n. Okay? Then, this is just a simplification of the notation. We are concerned with the convergence or divergence of the series is just the a sub n. Okay? So this is just notation to simplify our problem. So what we want to do to solve the question about convergence or divergence of this series is we're going to use the root test. So applying the root test, it's a very simple application here. We have the lim sup of the nth root of a sub n. And what's that equal to? That's equal to the lim sup of the nth root of the absolute value of c sub n, z to the n, which is the lim sup. I can break up this absolute value of these two complex numbers into the absolute value of the first and absolute value of the second. And really, even do more than that. I'll rewrite this as the absolute value of c sub n and the absolute value of z raised to b. And then that's equal to, well, the nth root of the absolute value of z raised to n is just going to be the absolute value of z. So it's the lim sup of z times the nth root of the absolute value of c sub n. Well, this is a constant with respect to n, and so this is going to be equal to z, the norm of z, or the absolute value of z, times the lim sup of the nth root of c sub n's inside absolute values. But that's equal to alpha, so that's equal to z times alpha, or norm of z times alpha, which is equal to the norm of z over r. Now what we know is that this is going to converge, provided this guy is less than 1. So thus, if z over r is less than 1, which implies that the norm of z is less than r, okay? Then the series C sub n z n converges. If the norm of z over r is greater than 1, that says that the norm of z is bigger than r, then this series, remember n running from 0 to infinity, diverges. And in both conclusions, it's by the root test. Okay, so that ends this proof. Now, I want to make some comments about what this theorem is saying. Now, this previous theorem implies that for every power series C sub n, z to n runs from 0 to infinity, that there exists an R such that this power series converges if the norm of z is less than r, okay? And diverges if the norm of z is bigger than r, okay? Because, as I said, this lim sup of the nth root of that's the value of c sub n times z n, this exists. And in this case, it's a number or infinity. Remember, it can't be minus infinity because we're talking about positive quantities here. So that lends us to one more definition. Okay, so the last thing I'll write is the following definition. So given a series, sum n runs from 0 to infinity of c sub n z to n, then the extended real number such that the series converges if normal z is less than r, and diverges if the normal z is bigger than r. This number is called the radius of convergence. For the series. And what we're going to be interested in is what we're going to know is what is R for a particular series. Now in Cal 2, we talk about finding the radius of convergence for a series of real numbers. And here we do the same type of thing for a series of complex numbers, except we don't get an integral as what we had before in Cal 2. And instead we get some kind of region in the complex plane. Anyway, we'll save examples for our next video lecture. Thank you very much for your time and patience.